Common source stage with resistive load. By virtue of its transconductance, a MOSFET converts variations in its gate source voltage to a small signal drain current, which can pass through a resistor to generate an output voltage shown in figure A. The common source stage performs such an operation. Here you can see the figure A. Common source stage. B. Input output characteristics. C. Equivalent circuit in deep triode region. D. Small signal model for the saturation region. We study both the large signal and small signal behavior of the circuit. Note that the input impedance of the circuit is very high at the low frequencies. If the input voltage increases from 0 M1 is off and V out equal to VDD. Figure B. As V in approaches VTH, M1 begins to turn on, drawing current from RD and lowering V out. If VDD is not excessively low, M1 turns out in saturation and we have V out equal to VDD minus RD 1 by 2 nu n C naught x W by L V in minus VTH whole square. Here channel length modulation is neglected. Channel length modulation is neglected with further increase in V in V out drops more and the transistor continues to operate in saturation until V in exceeds V out by VTH at point A in figure B. As this point V in 1 minus VTH equal to VDD minus RD 1 by 2 nu n C naught x W by L V in minus VTH whole square, from which V in minus VTH and hence V out can be calculated for V in greater than V in 1. M1 is in triode region. V out equal to VDD minus RD 1 by 2 nu n C naught x W by L 2 into V in minus VTH V out minus V square out. If V in is high enough to drive M1 into deep triode region, V out very much less than 2 into V in minus VTH, and from the equivalent circuit of figure C, V out is equal to VDD R1 by R1 plus RD is equal to VDD by 1 plus C nu n C naught x W by L RD into V in minus VTH. Since the transconductance drops in the triode region, we usually ensure that V out is greater than V in minus VTH. Operating to the left of point A in figure B, using equation as the input output characteristic and viewing its slope as the small signal gain, we have AV equal to dou V out by dou V in equal to minus RD nu n C naught x W by L V in minus VTH minus GM RD. This result can be directly derived from the observation that M1 converts an input voltage change delta V in to a drain current change GM delta V in, and hence an output voltage change minus GMRD delta V in. The small signal model of figure D yields some result. Even though derived for small signal operation, the equation AV equal to minus GMRD predicts certain effects if the circuit senses a large signal swing, since GM itself varies with the input signal. According to GM equal to nu n C naught x W by L VGS minus VTH, the gain of the circuit changes subsequently if the signal is large. In other words, if the gain of the circuit varies significantly with the signal swing, then the circuit operates in large signal mode. The dependence of the gain upon the signal level leads to nonlinearity, usually an undesirable effect. A key result here is to minimize the nonlinearity, and gain equation must be a weak function of signal dependent parameters such as GM. We represent several examples of this concept in this chapter and in chapter 30. How do we maximize the voltage gain of a common source stage? Writing equation as AV equal to minus root over 2 nu n C naught x W by L ID VRD by ID. Here you can see the figure. Here where VRD denotes the voltage drop across RD, we have AV equal to minus root over 2 nu n C naught x W by L VRD by root over ID. Thus, the magnitude of AV can be increased by increasing W by L or VRD or increasing or decreasing ID if other parameters are constant. It is important to understand trade-offs resulting from this equation. A larger device size leads to greater device capacitances and a higher VRD limits the maximum voltage swings. For example, if VDD minus VRD is equal to Vin minus VTH, then M1 is at the edge of the triode region, allowing only very small swings at the output and input. If VRD remains constant and ID reduced, then RD must increase, thereby leading to a greater time constant and the output at the output node. In other words, as noted in the analog design octagon, the circuit exhibits trade-offs between gain, bandwidth, and voltage swings. Lower supply voltages further tighten these trade-offs. For large values of RD, the effect of channel length modulation in M1 becomes significant, modifying to include this effect. Vout is equals to VDD minus RD 1 by 2 nu n C naught x W by L Vn minus VTH square 1 plus lambda Vout. We have dou Vout by dou Vn equal to minus RD mu n C naught x W by L Vn minus VTH into 1 plus lambda Vout is minus RD 1 by 2 nu n C naught x W by L Vn minus VTH square lambda dou Vout by dou Vn. Using the approximation ID similar to 1 by 2 nu n C naught x W by L Vn minus VTH whole square, we obtain AV is equals to minus RDGM minus RD lambda AV. And hence AV equal to minus GMRD by 1 plus RD lambda ID. Since lambda RD is equals to 1 by R naught, AV equals to minus GM R naught RD by R naught plus RD. This small signal model of figure gives the same result with much less effort. That is, since GM V1 R naught parallel RD is equal to minus V out and V1 equal to Vn, we have V out by Vn equal to minus GM R naught parallel RD. Note that as mentioned in chapter 1, Vn, V1 and V out in this figure denote small signal quantities. Here you can see the figure of small signal model of GS of CS, small signal model of CS stage including the transistor output resistance. Thank you.